Welcome back. We're here in section 2, and we'll split this up into 2 days as well. The first part, we're going to be looking at sample proportions, more importantly, sampling distribution of p hat, and of course, the normal approximation there in the first part. So let's get going here and see what we got cooking. All right, we have our learning targets that we have here, and we'll get through those as we go. Now remember, sampling distribution of the sample proportion p hat. It describes the distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. All right, so here's the approximate sampling distribution of the sample proportion of pennies from the 2000s in 50 samples of size n from a population of pennies, and that's what we get there. All right, now by the end of the section, you should be able to anticipate the shape, center, and variability of distributions just like this one. All right, so as we look at patterns here, always take a look at the mean and the standard deviation. Take a look at your population proportion, that's P, and then your sample, or your number size, your sample size here of 25. One thing you kind of notice a few patterns here, and we'll kind of point those out as we kind of go here. One thing we can see is that when n is small, so 25 is relatively small, and p is close to 0. We have 10% here. The sampling distribution of p hat is going to be skewed to the right. We can kind of see that. All right, and when n is small and p hat is close to 1, we have a really high proportion. The sampling distribution is then skewed to the left. Well, again, I think you can see what's coming is that when sampling distribution of p hat becomes more normal, when p is closer to 0.5 or n is larger or both. Okay, so in this case, we had n is 100 as opposed to 25. Our proportion is 50%, so those two things kind of bring that close together, being more normal. Okay, now the center, the mean of the sampling distribution of p hat is equal to the population proportion. It's equal to p. This makes sense because the sample proportion is an unbiased estimator of p. And there we go. We can kind of see that right there. That center lines up right there as we talked about that. All right, now variability. Now, as we talk about standard deviation of p hat, it depends on both n and p. So your sample size and your population proportion. Now, for a specific sample size, the standard deviation of that standard deviation of p hat is larger for values of p close to 0.5. And it's actually smaller for values of p close to 0 or 1. So as we kind of see here, that variability kind of goes as we have there. All right, larger, again, standard deviation is larger. You can see that right there. And then you can see that it is smaller. You can see that outlined right there. Okay, proof's in the pudding, as they say. All right, now for a specific value p, the standard deviation of p hat, the standard deviation of p hat gets smaller as n gets larger. Specifically, multiplying the sample size by 4 cuts the standard deviation in half, is what happens there. So it kind of makes a little more sense that the variability gets less as you get more sample sizes there. And you can kind of see that again as we go. Okay, so again, just rounding this out. So choose a simple random sample from a size n of a population of size n with proportion p of successes. Now, p hat is the sample proportion of successes. Then, that means is that the mean of that is simply just going to be the mean of the population. All right, the standard deviation is found by taking the population proportion of success times failure divided by your sample size, and then you take the square root. Now, that's as long, remember, as our 10% condition is satisfied. Remember that our sample size has to be less than 10% of our population. Okay, and the value of the standard deviation of p hat measures the typical distance between the sample proportion p hat and the population. So kind of the typical distance between the two of those is what we see there. Now the sampling distribution of p hat is approximately normal as long as the large counts condition is satisfied. So if you take the sample size times the population proportion, it's bigger than 10, and then the sample size times the failures proportion would be bigger than 10 as well. All right, so again, as we kind of highlight this, the two conditions mentioned on the slide are very important. Okay, now p hat is the sample proportion of successes. Now again, the large counts condition If we assume that in the sampling distribution of p hat is approximately normal when it isn't, then it's flawed, right? And that 10% condition, when we sample with replacement, the standard deviation of the sampling distribution of p hat is exactly that formula there. But without replacement, the observations are not independent, and the actual standard deviation is smaller than the value given by the formula. But if the sample size is less than 10% of the population size, then the formula is correct, okay? So here we go. Let's take a look at the problem that we have here. Suppose that 84% of students at a large high school regularly use a backpack to carry their books from class to class. Now imagine taking a simple random sample of 100 students and calculating p hat, which is the proportion of students in the sample who regularly use a backpack. Okay, so now what's our mean supposed to be? Well, again, we should see the mean of our p hat, again, is consistent with the proportion of the population, which is 0.84. All right, now the standard deviation, we use our little formula here. Success is 0.84. Failure, we take, be 0.16. Our sample size is 100. Divide that, take the standard deviation, and we get 0.0365. So what we're saying is in a simple random sample of 100, the sample proportion of students who regularly use a backpack typically vary by about 3.67% from the true proportion. That's the key word that we use. Remember we talked about that from the population, the true proportion, or the population proportion of 84%. Okay, now again, we're going to try to describe the shape now as we kind of talk about this now, because we take the n times p, that's 84, that's bigger than 10, and if we take n 100 times 0.16, that's 16. So again, by that rule, we can say that it is approximately normal in the case. All right, now when the sample size is large enough for n times p and n times 1 minus p to both be at least 10, large counts condition, the sampling distribution is normal. We just talked about that. Okay, in that case, we can use a normal distribution to estimate the probability of obtaining an SRS in which p hat lies in a specific interval. Okay, so here we go. Problem. Polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. Okay, so now let's take a look at what we're talking about here. So here's our true value, all right? We have 35%, so that's our mean of 0.35. All right, and we're going to assume, okay, yeah, 1,500, that's less than 10% of all first-year college. I think that's a safe assumption. So again, we take 0.35 times 0.65, success, failure, divided by our sample size, boom, 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 and this gives us the proportion of how far away our sample is going to be away from the true proportion that we have there, 0.0123. Okay, all right, so now, again, because that's true, because that 1,500 times 0.35 and the 1,500 times the 0.65, because those are both bigger than 10, we're going to assume that this is normal. All right, so here we go. We're going to take from 2 percentage points, so we're going from 0.33 to 0.35. Okay, that's the bottom end. Okay, that's 2 below. We're going to go 2 above. We're going to find those z-values, because now we just found the percentage here, right? And then, because that's the standard deviation of how far we would typically deviate from that true proportion, right? That's why we use the proportions here. That's why it's okay. So we're going from negative 1.63 to positive 1.63 using our table. And again, if we use those values, those z-scores, we will figure out that there is a percentage of 89%. Wow. And again, if you use the calculator, you can use that. Remember, you can use that as well. You get the same thing. All right. So there we are. And again, using all those different things from our calculators, we can compute all that stuff. So I like to use the z-tables. That's my preference, but different strokes for different folks. So, all right, so we're going to get some problems done with those to take advantage of those learning opportunities. It kind of really strikes home the vocab and then how those things really work. So take advantage of those, and then we'll come back next time and finish up section 2. Until next time, I'm Mr. Boone.